Hello, this is lecture 17. After a day's break, we went and did analysis of variance, or ANOVA. We studied the normal theory, also known as the F-test. We did multiple comparisons to Bonferroni method, a non-parametric Kruskal-Wallis test, and then did some in-class practice so you can see how to put the theory to use in R. So we're going to be focusing on a one-way layout. This is an experimental design in which independent measurements are made under each of several treatments. You should take a look at the example in the book for a one-way layout. So here we have 7 treatment groups. I is 7 and j independent observations per treatment group. We take a look at a box plot for each of the treatment groups, and although the middle line is the median, let's pretend for a moment that it's the mean, and what we're wondering is whether the mean for each of the treatment groups are the same. So is there a mu which is the same for all the groups? So that will be our null. Our null is that the differential effect for each treatment group, these alpha i's that you see in red here, they are all 0. So the question is, are the means of each treatment group the same, or is at least one of the means different? If there were just 2 treatment groups, we would be doing a t-test here. So we begin with the normal theory, the F statistic. So our picture is we have I treatments. I is actually generally written as the rows, and j independent observations are the y's, and our data are the yij's, and y bar 1 dot represents the average for the first treatment, and so on. Y dot dot represents the overall average of all the yij's, or also the mean of the means. So the model that we have here is our data, the yij, are a sum of 2 constants, an overall mean and a differential effect for the ith treatment, plus some random noise where this noise is normal 0 sigma squared. These differential effects are normalized so that they sum to 0, and what we see here is that the yij's are normal mu alpha I with variance sigma squared. Our null is that all the alpha i's are 0, so that the mean for each treatment group is mu, and the alternative is that not all the alpha i's are 0. So ANOVA is based on the theory, on this identity, that the sum of the squares total is the sum of squares within plus the sum of squares between. And so what this says is that you can think of the sum of squares total as the spread of values from the mean, from the overall mean. And we write this as, maybe we can best show it from a picture here. If you think about what's the overall variation here from the total mean, you can write that as a sum of 2 independent pieces. So the sum of squares within is, take a look at each of these treatment groups, the variance of the points for each treatment group, that spread, if we take so basically, so the spread from each of these treatment groups, that would be the sum of squares within, and another component making up the the total variance is going to be the variance of the mean. So if you look at the middle line here, you see that their position varies. So basically the spread of these treatment means from the total mean, that is the sum of squares between. So we have this decomposition here, and this decomposition is very important to understand, and we'll see it again in regression. So you can write out what the formula is for this, and the proof of this is algebraic, and it's in the book, and you should read that carefully. But actually, it'll be more instructive to work through an example. But before we do that, should note that the sum of squares within and the sum of squares between are independent, and that follows from an argument here using a result from chapter 6. So here's an example where we have a very simple situation where we have 3 treatment groups and 3 independent observations per treatment group. The average for the first treatment is 2, for the second treatment is 4, and for the third treatment is 6, and the overall average is 4. Remember from chapter 6, we discussed early on in the course that the sample variance divided by the population variance times the sample size minus 1 is chi-squared with n minus 1 degrees of freedom. So the sum of squares total, so that is each element, each of your data elements minus the overall mean quantity squared summed over all of your data, and that turns out to be 30 here. And furthermore, the sum of square totals has degrees of freedom ij minus 1. The sum of squares within consists of looking at the difference between each element, each treatment element, and the treatment mean for each of the treatments. And furthermore, so that turns out to be 6, and through some calculations here, you can show that this has ij minus 1 degrees of freedom. And then the sum of squares between, so here what we're looking at is the difference between these means, 2, 4, 6, and the total mean. And we do this for each element of our data. So for example, for the first row, we would have 2 minus 4 quantity squared. And then for the second element, 2 here, we would also write 2 minus 6 quantity squared. 2 minus 4 quantity squared, and so on. So we see that the sum of squares between is 24, and some calculations then lead us to show that SSB has I minus 1 degrees of freedom. So we confirm that indeed SST is SSW plus SSB, 30 is 6 plus 24, but more is true because we've shown that these sum of squares, SSB and SSW, are independent, and SSB over sigma squared is chi-squared, and SSW over sigma squared is chi-squared. So we're adding independent chi-squared, so their degrees of freedom add up. And indeed, we can confirm that 6 plus 2 is 8. So we need to introduce the F distribution from chapter 6. So F is defined as the ratio of two independent chi-squares divided by their respective degrees of freedom. And that's exactly what we have here. We can write F as SSB over sigma squared over I minus 1, which is chi squared, divided by I minus 1 degrees of freedom. And SSW over sigma squared is chi squared with j minus 1 degrees of freedom. So so there you go, and you can calculate this to be 12. So what F values do you predict? Well, this is a nice theorem from your book that shows that if you look at when the null is true, so when the null is true, if you look at the expected value for SSB, when the null is true, this alpha I squared term vanishes, and you're just left with I minus 1 sigma squared. And so the expectation of SSB over I minus 1 then is sigma squared. So SSB over I minus 1 is a unbiased estimator for the population variance under the null. And furthermore, SSW over ij minus 1 is also an unbiased estimator. So their ratio then should be close to 1. And so you expect, if the null is true, that f is going to be close to 1. However, if the null is not true, then that means that some of your alpha i's are positive, which will make the expected SSB larger. So the expectation of SSB over I minus 1 will be greater than the expectation of SSW over ij minus 1, because the expectation of SSW doesn't have any alpha term in it. So the expectation for the numerator of the f term will be larger than the denominator when the null is not true. So in that case, you expect f to be greater than 1. So now we got a score of 12, right? So likely we're going to reject. So this is a picture of the F26 distribution, which is what we're looking at in this example. And so we got 12, and we can compute the p-value. We can compute the p-value using the shown r command here, and we receive, and we show that that's 0.008. So the f-test is a one-sided test, similar to chi-squared, and if we make alpha equal to 0.3 for some reason, that will just make the numbers nicer later, then clearly we would reject the null, since 0.008 is smaller than 0.3. It's also important to be aware that although our treatment groups have all been the same size, that's not necessary. So the treatment groups can have different sizes, say J1 to Ji, and we have then some different formulas for SSW and SSB and F. But this is all straightforward, and I think I'll just let you read this. So at that point, we took a break, and